So in this section, we're going to look at the practical side of working out the heat of combustion of these fuels. So this is an experiment that you're going to do next week. Normally we would do it at this point in your learning, but yeah, I'm not there with you. So if we burn a fuel under a container of water, hoping that the majority of the energy is going to transfer to that water, then the energy absorbed by the water is a good approximation of the energy being released by the fuel. Now, I'm hoping that you've already seen a real downside to this, that this is a very inaccurate method, because a lot of the energy is lost to the surroundings, it's lost to actually heating the can. It's quite inaccurate, but nonetheless, it's an excuse for an experiment. So the energy absorbed by the water is calculated using the equation that we met back in year 11, Q equals mc delta T, where Q is the energy going into the water, M is the mass of the water, C is the specific heat capacity, 4.18 of water, and that's in joules per gram per degree Celsius, and delta T is the change in temperature of the water. So this is all about the water. Example is given here. We're wanting to heat this water to boiling point, so that's why the delta T has to be 100 minus 15, because we're starting at 15 and we want to get up to 100 degrees. So that's 85. And we multiply the mass of the water, because the density of water is best expressed as 1.00 grams per milliliter. If we express it to 3 decimal places, then in the data book, I think it's 0.987 or something, but generally speaking, it's 1.00. Then that's that 0.987 is also only at 25 degrees Celsius, and this doesn't apply here. So mass times specific heat capacity times the change in temperature, in this case, is going to give us 53.3 kilojoules. That temperature probably should have been expressed as 15.0, because I never intended this question to be 2 significant figures. So this is what the experiment you will do will look like. We'll have a spirit burner with methanol in it. So spirit burner containing methanol, and there is a can of water above the methanol. We know how much water is in that can. There's a thermometer in the water. Now we can use our data logging here, which makes life a whole lot easier. And the can is heated by the burning spirit burner. So let's look at the calculations that are involved here. So we want to link the energy that's being absorbed by the water, and that value is Q, to the amount of fuel that is burnt. Now we can measure the mass. Oh, that shouldn't be a T, that should be an M. Okay, so the change in mass, delta M, of the fuel gives us the mass that we'll use in our calculation of mole, N equals little m over big M, because the mass of the fuel being used is the delta M that we measure. And then we're going to use the relationship that we've already met in this chapter. Delta H over the number of mole that goes with the delta H is equal to Q over the number of mole that goes with the Q. And Q is the same as E. We're playing around here with Q's and E's and things. Really, it doesn't matter greatly. No, don't worry too much. Maybe just use Q all the time. And so this, because N1 was equal to 1, delta HC, our heat of combustion, our enthalpy of combustion, is equal to Q divided by N. So the energy into the water, Q, divided by the amount of fuel that created that energy. So here's a little summary of what you're going to need from a heat of combustion experiment. You're going to need the initial mass of the spirit burner, of what you're burning your fuel in, and the final mass. And the change in mass is going to be the mass of the fuel that's burnt. Then you need the mass of the water so that you can use it in Q equals mc delta T. And you need the initial temperature of the water and the final temperature of the water, once again, to be able to use in Q equals mc delta T. So the calculations you're going to be doing, some of them simple, some of them a little more complex. Change in temperature, calculation of Q, then the change in mass of the fuel from the weighing before and after, and the amount of fuel that we work out from that mass using the molar mass of the fuel. And then finally you put it all together, and the delta H, the heat of combustion of the fuel is Q divided by number of mole that caused that Q. All right, so pretty straightforward. And as I said, we'll be doing this experiment next week, and it is indeed the first experiment of the SAC. So this is why I want you to be prepared. Here's the worked example from the textbook. We've got 0.355 grams of methanol undergoing complete combustion. The energy released heats 100 ml of water. You've got your temperature change of the water, and we want to calculate the heat of combustion. So we've got delta T, and this is being quoted to 4 significant figures, which is very lovely. And our Q equals mc delta T. Strictly speaking, we've now been cut down to 3 in our final answer because of the 100 and the 4.18. Now, you might say, well, if we had measured the mass of the water instead of the volume, that would have made things more accurate. But the bottom line is that the specific heat capacity is 4.18 no matter what. So maybe it doesn't matter that much. Then Q is the energy from that 7.277 kilojoules. We find the amount in mole, and that's dividing the mass by the molar mass of methanol, and then we do the division. Now, you don't have to put your negative in at this point as shown here. You can wait until the end. And the end is the equation. So the equation that you're going to end up with is for the combustion of 1 mole of methanol. And I would like you to stop the video at this point and actually write that equation before you check what I've written. So coming back, we have 1 carbon dioxide, 2 waters, and I'm going to need 2, no I don't, I want 3/2 oxygens there. Now the reason for that is there's 1 oxygen in the methanol, so we're going to write 3/2 so that we keep our 1 mole of methanol there, and then the delta H for that equation is, and this is the most appropriate place to put your negative sign, 656 kilojoules per mole. So that's the thermochemical equation for that reaction. Now, there's a worked example, there's a try yourself example to do there. This is from your textbook on page 58, and that is the end of chapter 2. You should be able to manage all the questions now, and if necessary, there's Volk Science videos to watch or a video to watch. Keep working on your summary, writing the 3 main points, and there's worked exam questions, and of course the checkpoints questions as well. There's an awful lot here to do. I want you to do as many questions as you can before I see you next week, but we'll discuss when they're to be handed in. So they're not all going to be due in our first lesson next week, but let's say by the end of the week. Right. Well done, everybody, including me.